So the first thing I want to talk about is, this was something that we did in lab last week, but I just want to get it in your notes. So a big part of what we're doing with particle kinematics is free fall problems. So there's a big focus on free fall. And free fall, to use the approach for free fall, it assumes that there's no significant air resistance. It assumes air resistance is negligible, or air resistance has a negligible effect on the motion. And so it's always a good idea to keep in mind when that assumption is reasonable and when it's not. So when is this assumption valid? And there's no real hard answers to that. It depends on a few things. And one of the things it depends on is how precise do you want your estimate to be. But the things that you should keep in mind, here are the things that affect let's say that cause an air resistance effect on the motion. In a fall. Not in the fall. It works all year. Thank you. Forget the rest of you guys. Okay, so the first thing is an object's mass. If all the other things that I'm going to talk about stay the same and the mass is bigger, a larger mass means a reduced effect of air resistance. The reason is that the drag force is overwhelmed by the weight force. So if you're thinking about two objects that have different masses and everything else stays the same, think of a ping pong ball versus ping pong ball sized piece of steel ball. If you drop both of those off the roof of a building, which one would hit the ground first? Yeah, right. It has more mass, and so air resistance is going to affect its fall less. So even though those two balls are identical in every other way we're going to talk about, the mass means that the weight of the steel ball overwhelms the drag force that even though it's actually the same drag force that the air produces on both of them. On the steel ball, it has less of an effect. Second thing is speed. Um, as you increase the speed, there's a greater air resistance effect. And this is the only variable in that equation. I don't want you to memorize that equation from the lab or anything, but if you look back at that equation, speed is the only one that shows up squared. Everything else is linear in that equation. So there's a pretty abrupt change in air resistance as the speed increases. One place you see it is, this used to be maybe a more people felt like they knew what I was talking about when I said this. It used to be like when Lance Armstrong was good and hadn't admitted to drugs yet and whatever, like bike racing was really big for a while here. But have any of you ever watched like Tour de France races or whatever? Okay, so in the Tour de France or big races like that, they do a race every day and they're all different kinds of races. But there's really only a couple of those kind of races where you can make up any time. Otherwise, everybody just huddles together to reduce the air resistance effect. And so the main way that you can make up time is in time trials. So in time trials, you know, they're not allowed to bunch together. Someone goes every 3 minutes, someone takes off, and they just time people. And so the fastest you can go by yourself, the faster you can go by yourself, the better you do in the time trial. In bike racing. And there are two kinds of time trials that they do. Some are flat, you know, just going through towns or whatever. And some go up the Alps in the Tour de France. And in the flat time trials, they ride these bikes that are barely recognizable as bikes. They have like everything has streamlined stuff in front of it. They ride their bikes in a position like, let's see. Okay, so something like that. They wear these helmets that go down their back like that, right? They even wear little visors on the front of their helmets. Let's see. Can I make a bike out of this now? Yeah. So this is what they look. Oh, and they're wearing like these rubberized suits. You know, and even in designing these bikes, like I like bikes and stuff. So I was reading a book about racing, and one guy was criticizing one of the teams he was racing against, and he's like, it was like they weren't even trying, that they had their cables flapping in the air. I think he said something like that. And what he's talking about is those tiny little cables that connect the brakes and the shifters to the stuff in the back. They're steel, so they're not flapping. They're rigid, and they're this big around. And they put so much effort into reducing air drag that they make sure that those either go perfectly along the lines of the tubes normally, or even inside the tubes. And so he was just like, he couldn't believe that this team had those little cables exposed to the air instead of going through. Like, that's a pretty extreme interest in cutting down drag, right? That's all I'm trying to say. Look at this guy. Everything about the way he's riding, like, is this stuff chosen to maximize how much force he can apply to the pedals? No, it's mainly chosen just to reduce drag as much as possible. And then compare that to what they look like when they're doing a mountain time trial. So here's the Alps steep, and here's their bike. They ride bikes now that just look like normal bikes. They don't even get down in the drop bars. A lot of the times they'll have their hands up on the bars. You know, they look they're way fatter. No, that's not true. They wear regular helmets. They just look like people out for a bike ride. And so why is that? I mean, they're exerting themselves the same amount in both cases. You know, they're not wearing the rubberized suits. They're wearing regular jerseys, and most of the time when you look at them, their jerseys aren't even zipped up. They're just open to cool them down, and they're, you know. So what's the difference? It's not that this is harder and they need, you know, the difference is just in the small change in speed between, I mean, relative to bike races, it's a big change in speed. But in these flat time trials, they're going, say, 35 miles an hour. And these mountain time trials, they're going 20 miles an hour. And just that relatively small change in speed is the difference between air resistance being the entire story to air resistance being relatively unimportant. So, interesting, right? Thank you. Thank you, thank you. And then the last thing that matters is the shape of the object. And if you have a shape where more area is available to catch air, or a less streamlined shape, and those are actually different things. Then you have an increased air resistance effect. So an example of this is, let's say a 30-gram ball versus 30 versus 30-gram, you know, army man with a parachute. Not a real one, like a toy. I'm ready to fight. Put me in. I want to serve this country. So, which of these would more approximate the motion that we expect based on our free fall equations? The ball, even though they have the same mass, the parachute has this, I mean, it's designed to have a shape that is not streamlined and presents a big area to the air. And so this is hugely affected by air resistance. That's what it's made for, and the ball doesn't. Any questions about that? Any more questions about bike racing or the Tour de France? Okay. Well, let's do a couple more example problems. Um, so let's say that, did we do this one last time? Did we do one at the end of last time where a ball was rolling up a ramp? Okay. I ring that bell whenever I'm going to do a problem involving a ball rolling on a ramp. At your AP test, I'm going to be in there with a bell trying to signal you. A ball on a ramp. Remember what I said. Okay, so a ball rolls up a ramp. When it passes point A, it's moving, let's say, 4 meters per second. At point B, it's moving 2 meters per second. And it takes 1 second to get from A to B. So first, how far apart are A and B? And second, what's the acceleration? Okay, go do it on the board. All right, so the first thing we're asked for is how far apart are these points? Let's choose our time equals 0 instant to be when it passes A. Our time final instant to be when it passes B. Our position equals 0 is A, and our positive direction is up the ramp. So we're trying to find the position when it reaches point B. So we're trying to find PF. We know that TF is 1 second. We don't know acceleration. P initial, or P sub 0, is 0. V sub 0 is 4 meters per second. How do we know that this is positive and not negative? Yeah, that's right. It's going up the ramp, so that's our positive direction. V final is positive 2 meters per second. And that's everything. So now what we're looking for is an equation that has PF in it, and all the other variables in it are listed here. Are there any that work like that? No. So let's try to solve, since the first thing we wanted to do didn't work in one step, we need to find another variable to solve for, an intermediate variable that we can then plug in. So the one that you usually want to find is, there are two likely ones, time final and acceleration. So we'll try to find acceleration first. Okay, so is there an equation that lets us solve for acceleration? Yeah, we can use this one. Vf is equal to v sub 0 plus atf. That says 2 meters per second is equal to 4 meters per second plus 1 second times a. And that gives you that the acceleration is negative 2 meters per second squared. So that's the answer to part B. Now we'll try part A again. Now that this acceleration is known, and there are two equations you can use to solve for part A now. I'm going to use the one that says PF is equal to P sub 0 plus V sub 0 TF plus 1/2 A TF squared. So PF is equal to 0 plus 4 times 1 plus 1/2 times negative 2 times 1 squared. And you get that PF is equal to 3 meters. And then for part C, we're trying to find when it reaches the highest point on the ramp. So before I do that, let's think about those things that we have to choose before we can start the problem. The time equals 0 instant, the time final instant, the position equals 0 location, and the positive direction. Is there any reason to change what we're calling our time equals 0? Nope, there's no reason we have to. We also know a bunch of stuff at B, and so if you wanted to, you could do this problem by changing your time equals 0 instant to be at B, but it would just be making it unnecessarily complicated. So reaches A, that's the same as before. But we do have to change the instant we're calling time final. You can only calculate variables at your time equals 0 instant and at your time final instant. So, so if we're trying to find something when the ball reaches its highest point, we're going to have to make that our time final. Position equals 0, call that A again. Positive direction, call that up the ramp again. So the only thing we had to change was what we're calling our time final. Do we know time final? Numerical value? No. Do we need it? No. If we can get away without it, that's good. Fine. Do we know the acceleration? Yeah, that's going to stay steady through the whole problem, even though we changed what we're calling our time final. And that's because these equations only work when the acceleration is constant through the whole thing. So A is equal to negative 2 meters per second squared. Our position when time is equal to 0 is 0. Our final position is what we're trying to find. Do we know the velocity when time is equal to 0? Yeah, that's positive 4. V final, what's V final? 0. So that's how you specify that it's at its highest point. That's the requirement for highest. Is there an equation that works with these? I think this one should work. 2a times the quantity pf minus p sub 0 is equal to vf squared minus v sub 0 squared. So we have 2 times negative 2 times the quantity pf minus 0 is equal to 0 squared minus 4 squared. So we have negative 4 pf what? Oh, 4 squared, yeah, is equal to negative 16. And so pf is equal to positive 4 meters. Any questions about that? All right, let's do one more. So let's say an object is launched into the air. From a height of p sub 0 with an initial velocity of v sub 0. And we want to know what's its maximum height. What's its velocity when it reaches a height of p sub 0 on the way back down. And third, what's its velocity the instant before it hits the ground. All right, so first we have to make those 4 choices. Our time equals 0 instant is going to be when it's launched. Time final for part A is when it reaches the max height. Our p equals 0. Usually for these free fall problems, I choose p equals 0 to be the ground or whatever is the sort of the base of the, if it's over water, I choose it to be the level of the water. You can do it That's not required. You can do the problem fine with whatever choice you want, but I'm going to choose p equals 0 to be the ground. And then positive direction, I always choose to be up in free fall problems. Okay, so do we know time final? Nope. Do we know acceleration? Yeah, that's acceleration is g pointing down. And since our positive direction is up, that means that's a negative g. Do we know the position when time is equal to 0? Yeah, so P0 is P0. Wouldn't it have been confusing if I would have told you that like the starting position was the variable P final and stuff like that? I just, that would have been rude. P final, do we know that? Do we want it? Yes. V initial, velocity when time is equal to 0. That's V0, and it's going up, and our positive direction is up, so that's positive. And then V final. Yeah, we're looking for the highest point, so that's 0. And the equation that works with all these, of those 3 equations I gave you, there's only one of them that doesn't have time in it. So if you don't know time, there's only one that has a chance to work, and it's this one. And so the only thing we have to substitute, almost all of these stay the same name, except A is equal to negative G. And VF is 0. So we have 2G times the quantity PF minus P0 is equal to V0 squared. And so PF is equal to P0 plus V0 squared over 2G. Any questions about that? Okay, for part B, we're trying to figure out how fast, what the velocity is of the object when it passes back, when it passes its starting point again. Is there any reason to change any of these choices about the problem? There's one we have to change. All the rest can stay the same. Same. But we have to change what T final refers to, or we'll only be able to calculate stuff at the highest point. So now we're going to choose TF to be when the object reaches the height P sub 0. Since T0, P equals 0, and positive direction stay the same, all the initial stuff that we knew stays exactly the same. Time final, we don't know. Acceleration is negative G. P0 is P0. P final, what's P final equal to? P0, that's where it gets a little confusing. V0 is positive V0. V final is what we're trying to find. And it looks like it's the same equation that we'll want for this. 2a times the quantity pf minus p sub 0 is equal to vf squared minus v0 squared. So that says negative 2g times the quantity p0 minus p0 is equal to vf squared minus v0 squared. The left side goes away, and we end up with vf equal to plus or minus v0. On the way back down, our positive direction is up, so we want the negative one of those. And actually, in a free fall problem or any projectile motion problem, if you're neglecting air resistance, at any given height, the speed is the same on the way up that it is on the way down. You can think of that if those velocities are slopes of the tangent lines, and so you can think of that as a consequence of the symmetry of a parabola. And so one thing that says is it explains why it's a really bad idea to shoot guns up into the air to celebrate New Year's or whatever. I mean, there's a lot of air resistance on a bullet, obviously, but if you neglect the air resistance, the bullet comes back down to Earth at exactly the same speed it was shot up, and that's quite a large velocity. It can cause severe injury, etc. Yes? Oh, yeah? Huh. I've never seen that one. Well, I'll show you one later, actually. Have you seen the one where they shoot a bullet at the same time they drop a bullet? So we'll see that one later when we talk about two-dimensional kinematics. But yeah, they have some really good videos. A bullet is pretty streamlined, but it doesn't have a lot of mass, and it's going very, very fast. And so there's a ton of air resistance slowing it down, which means that by the time it comes down to Earth, it's going a lot slower than it took off. But either way, it's coming back down to Earth really, really fast. And then part C. Now we're looking for the velocity right before it hits the ground. Is there any reason to change any of these choices? Well, again, 3 of these can stay the same, but we do have to change what we're calling time final to be right before it hits the ground. We don't know time final. The acceleration is negative g. The position at time equals 0 is p0. What do we know about the final position right before it hits the ground? 0, yep. What we've specified here is that the point that we're labeling as 0 is the ground. So when something returns to the ground, it returns to a position of 0. Initial velocity is 0. Final velocity is what we're trying to find. And it's going to be the same equation again. So 2a times pf minus p sub 0 is equal to vf squared minus v0 squared. And so if you substitute in, you get negative 2g times the quantity 0 minus p0 is equal to vf squared minus v0 squared. So 2g p0 is equal to vf squared minus v0 squared. So vf is equal to plus or minus square root of v0 squared plus 2g p0. And which of these do we want, positive or negative? Negative, because we chose our positive to be up and this is going down. Any questions about that? Okay, there's one last topic we need to talk about with particle kinematics in 1D, and that's relative motion. We've taken all of our position measurements have been based on where we set down a ruler. You know, what we choose is our zero position, which direction we have the positive. So now the question is, what if there are two different rulers? Is there a way to use measurements in one to give us measurements in another one? So what do we know about the relationship between one ruler's measurements and the other's measurements? Okay, so let me draw the picture. So let's say we're tracking the motion of this particle P. You know, it's doing its thing. And we have two ways of measuring that. Let's say this is the ruler A, where that's the zero, that's the positive direction. And this is the ruler B. So based on this, looking at the position of that particle in the picture I drew, this ruler A says that the particle P has some positive value. If I drew out all the numbers, we could figure out what that position is. And the ruler B says that that particle has a negative position. That just has to do with the with where those zeros are. So the first thing we need to do is come up with a way to describe these two different measurements. So the first thing we have to do is name these differing measurements. So the measurement of P according to ruler A, we're going to call P with a subscript P over A. Okay. First P is for position. The second one is for, it's the position of that particle P. And the third one is for ruler A. And in words, we're going to call this the position of P relative to A. And so the position according to ruler B is just position of P relative to B. And notice that just like you can give positions of that particle P according to each of those two rulers, you could also use one ruler to tell you the position of the other ruler. So the measurement of the position of ruler B's 0 according to A, according to ruler A, what do you think we're going to call this? Position of, it's a measure of the position of B according to A, so it's the position of B relative to A. And the relationship between all these measurements says the position of P relative to A is equal to the position of P relative to B plus the position of B relative to A. As a memory device, this isn't really based on real math. It makes it easy to remember the order that these have to go into. Think of fraction multiplication. P over A is equal to P over B times B over A, right? These two cancel and that fraction works out. These work similarly for velocity and acceleration if those rulers aren't just sitting there, if those rulers are also moving. They work for velocity and acceleration too. So the velocity of P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. And for acceleration, the acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. Okay, so let me show you how you would use these equations. So the first example, let's say that an airport walkway moves 3 meters per second. And one particular late passenger can run 8 meters per second. That's pretty good. That's hammering. I don't think they could hold that very long. That's like that's like 18 miles an hour or something. Okay, well, those are the numbers I have in front of me. It's Usain Bolt, like the Olympics. That's like if you could keep that up for a mile, that would be like a 3 minute and 30-second mile. And so what's the speed of the passenger according to a camera on the ground? Okay, so the passenger is on the walkway running 8 meters per second. That's a really fast walkway, too. I think I was thinking of miles per hour, probably. So how does this go together? Well, the velocity of the passenger relative to the ground is equal to the velocity of the passenger relative to the walkway plus the velocity of the walkway relative to the ground. So the velocity of the passenger relative to the ground is what we're trying to find. And that's equal to, what's the velocity of the passenger according to, say, there was a camera fixed on the walkway measuring the passenger running? That's right, 8. And what's the velocity of the walkway compared to the ground? That's 3. And so the velocity of the passenger that would be measured by somebody on the ground is 11. What if the passenger was super dumb and was sprinting on the wrong walkway going the other direction? How would this work out? Well, yeah, like a treadmill. Then these would be in opposite directions. And so you'd have passenger walkway plus 8, walkway ground -3, and you'd have a net of 5 meters per second measured on the ground. Okay, let me do one with acceleration, and then that's it for today. So let's say that an elevator is accelerating up 1 meter per second squared when an object is dropped. what's the apparent acceleration? How do you spell apparent? 2 P's? Apparent acceleration of the object observed by someone on the elevator. Well, the object's in free fall. So we know that the acceleration of the object relative to the ground is negative 9.81 meters per second squared. We know the acceleration of the elevator relative to the ground is positive 1 meter per second squared. So the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the elevator plus the acceleration of the elevator relative to the ground. So we have negative 9.81 is equal to the acceleration of the object relative to the elevator plus 1. So rearrange these and you see that somebody watching on the elevator or a camera on the elevator that's measuring this sees an acceleration of negative 10.81 meters per second squared. So to somebody on the elevator, this acceleration, the fall of this thing looks funny because of the acceleration of the elevator. Yep.
So I'm is it like just watching from the elevator as something outside of it is dropped?
No, something inside the elevator is dropped. But even in the elevator, gravity still does the same things to objects, you know. So somebody in the elevator drops their purse or whatever, and what they see is an extra strong acceleration of the object, even though what's really happening is just that the object's accelerating that way while the elevator's accelerating that way. Okay. Any other questions? Okay, that's it. Oh, I need your help.